Hello. In this video, I would like to discuss about the catalysis. Before that, a small topic which I left out in the previous video is integrated rate equation for nth order of the reaction. If you consider a reaction only with one reactant, that reaction happens with only one reactant, a general rate law can be written as the dr by dt is equal to k into r raised to n. So if you rearrange it, you can write it as dr by r raised to n is equal to k dt. If you integrate it, this is actually r naught, the r naught to r, so that you will be getting an expression like this. If the reaction is not first order, so that n is not equal to 1, the integration of this equation could be done like this. So it will be like this: minus 1 by minus n plus 1 into molar concentration of r raised to minus n plus 1 with respect to r naught and r. Then if you simplify it, it will be like this. And again, if you simplify, it will be like this. And so that you can get a standard equation for the integrated rate equation, for the integrated rate equation, that is for nth order reaction. This is simple. If they ask, you can write down this. And the next concept is steady state of the reaction. What does it mean? It is an approximation actually. When you work out with the mechanism of the reactions, where the complex kinetics is involved, it is not easy to solve. So we make a few approximation. Out of that, one approximation is steady state of the reaction. So a reaction is in the steady state if the rates of the loss of all the reactants and the rates of the production of all the products which appear in the balanced reaction equation are equal. That means there will not be any possibility for the formation of intermediate. It's not the possibility. The concentration of the intermediate is very low. Consider a reaction that is A moles of A gives B moles of B to give G moles of G and H moles of H. So you can write down the expression for the rate of the reaction like this. In the other words, it means that the intermediates are present at very low concentration and the rate of their products and the low products and the loss are equal. That means whatever be the amount of reactants are getting consumed or whatever be the products are getting produced are equal. There is no stack up of the reactant in the form of intermediate. That is what the steady state approximation. So the consequence of the steady state approximation is, so I means intermediate. The steady state concentration of the intermediate is far lesser than the steady state concentration of the reactant A, reactant B, reactant C for this particular reaction. Then you can write down the rate of change of molar concentration of the intermediate produced is equal to rate of change of molar concentration of the intermediate consumed. So what happens if you consider the reaction? The possible reaction mechanism is A plus B gives I intermediate, and this I reacts with C, so that then only 3 reactants can react in order to give D. So the rate expression could be written like this for the formation of intermediate, and the formation of for the conception of the intermediate rate expression could be written like this. So what is the advantage of writing like this if you ask? So we'll take all the reactants and products into consideration. So you can write down the equation like this. And if you could write the molar constant, the rate of the reaction with respect to the molar concentration of the intermediate, you can write it like this: di minus dt, that means the molar concentration getting produced, is equal to molar concentration of rate of change of molar concentration of the intermediate consumed. It is supposed to be negative. This minus this is supposed to be 0 if it is steady state approximation. So that you can even write like this with respect to this equation. So rate of change of molar concentration of A with respect to time, means rate of change means it is with respect to time, minus change in molar concentration of D by dt is equal to 0. See here, you could see that it is taken magnitude, so that we can generalize like this: the intermediate rate of change of intermediate produced is equal to rate of change of intermediate consumed. So when you are stuck up with certain equations which is not able to solve, you can use this expression and it will help you to solve it in an easy way. So what is steady state approximation? It is the assumption that steady state approximation, that is the rate of change of molar concentration of the intermediate produced, is equal to rate of change of consumption of the molar concentration of the intermediate. So the steady state approximation is the most common approach to the analysis of reaction mechanism. So if they ask you what is steady state approximation, the steady state approximation assumes that after an initial induction period, an interval during which the concentration of intermediate, that is I, rise from 0, and during the major part of the reaction, the rates of the change of the concentration of all the reaction intermediates are negligibly small. And you can write this equation also. That means during the course of reaction, even though the intermediates are formed, the molar concentration of the intermediate is negligibly small. This is what we call steady state approximation. Then very interesting question is, how do you distinguish between the transition state and the intermediate? So suppose if you take this reaction, just like in the previous case, A plus B gives an intermediate and the intermediate and B reacts to give C. So if you plot the energy profile diagram, it is like this: A plus B represents this area represents the reaction intermediate, and this area represents the products. Whereas these two are the transition state and this is the intermediate. So intermediate means it is the entity, it's a species which exists.
It has got a discrete lifetime. It exists even though it is for few nanoseconds. Whereas for transition state, one vibration cycle, that's it.
So next topic is catalysis. So every catalytic reaction, so what is catalysis means? Catalysis is the process in which certain substances enhance the rate of the reaction without participating in the reaction. So every catalytic reaction is a sequence of elementary steps in which the reactant molecules bind to the catalyst, where they react, after which the product detaches from the catalyst, liberating the latter from the next cycle. So this catalyst is binding to the substrate is binding to the catalyst so that it gets like this, and here the reaction process happens. Then what will happen? The reactants, the product is getting detached from the catalyst. So how does it happens? Like the catalysis enhances the rate of the reaction. Catalyst suggests an alternative path of the reaction by lowering the activation energy than that is required for uncatalyzed reaction. There are three sub-disciplines of catalysis. One is homogeneous catalysis, heterogeneous catalysis, and biocatalysis. Actually, biocatalysis more or less homogeneous catalysis only. We'll illustrate each with example. Homogeneous catalysis, both the catalyst and the reactants are in the same phase. Ozone in the atmosphere decomposes among other routes by the a reaction with the chlorine atom. So Cl plus O3 gives ClO3. ClO3 reacts to give ClO and O2, and this ClO again reacts with another oxygen to give Cl plus O2. During the, if you look at the overall reaction, it is like this. O3 plus O gives 2O2, and the chlorine is nowhere in the overall reaction. So chlorine enhances the rate of the reaction without participating in the chemical reaction. Another example is the catalytic carbonylation of methanol to acetic acid. CH3COH plus CO gives CH3COH. It happens in presence of a rhodium complex. What are the features of homogeneous catalysis? Homogeneous catalysis most of the time happens in aqueous phase. So when it is aqueous phase, more or less it could be an acid or base. So when it is an acid or base, they have very good scope for polarization of the substrate. The advantage of homogeneous catalysis is that the catalyst mixes into the reaction mixture, allowing a very high degree of interaction between the catalytic and reaction molecules. So when it is in the aqueous solution, they have very good mobility. When they have very good mobility, there is a great possibility of the reactants which are supposed to react to meet each other. So that's what meant by high degree of interaction. However, unlike the heterogeneous catalysis, the homogeneous catalysis is often irrecoverable after the reaction has run to completion. That means, like if it is a solid catalyst, you can recover the catalyst once the reaction is over. But in case of the aqueous solution, once the reaction is over, the catalyst will be there without participating in the reaction, but recovering it is difficult because it's already dissolved in aqueous solution. Homogeneous catalysis are the used variety of industrial applications as they allow for an increase in the reaction rate without an increase in temperature. That is one more advantage. Next is biocatalysis. If you are a biologist, you will call the catalyst as enzymes. Enzymes are the nature's catalyst. For the moment, it is sufficient to consider the enzymes as a large protein, the structure of which results in a very shape specific active site. So the enzymes are special proteins or nucleic acids having an active site which is responsible for the adsorption of the reactants or the substrate and process into the products. Most of the time the RNA molecules will be the example for the enzymes. Best example is ribozymes. These ribozymes synthesize protein in the cell. And the very important feature is the structure of the active site that is very specific to the reaction. Having shapes that are optimally suited to guide the reactant molecule, usually referred to as substrate, in the optimum configuration for the reaction. Enzymes are highly specific and efficient catalyst. The enzyme's catalase is an example. Catalyzes the decomposition of hydrogen peroxide into water and oxygen at the incredibly high rate of up to 10 raised to 7 hydrogen peroxide molecule per second. This is an example. So if you look at the enzyme action, there are two models for the enzyme action. One is lock and key model, that is complementary three-dimensional structure is there for the catalyst which can occupy the substrate. One more is the induced fit model. This is what can actually fit into this area, and this part is can fit into this area. So it's like lock and key. So you could see over here the substrate 1 and substrate 2 is attached to the enzyme, that is the catalyst, and after once the product is getting formed, the product is separated from the catalyst. Schematic representation of an enzyme catalyzed reaction. Enzymes often match the shape of the substrate they bind to or the transition state of the reaction they catalyze. Enzymes are highly efficient catalysts and represent a great source of inspiration for designing technical catalysts. So if you look into the lock and key model and the other one is induced fit model, two models that explain the binding of binding of a substrate to the active site of an enzyme. In the lock and key model, the active site and the substrate have complementary. See over here, this part and this part, the space, have complementary three-dimensional structure and dock perfectly without the need for the major atomic rearrangement. Whereas in case of the induced fit model, binding of the substrate is induced a conformational change in the active site. This is what the active site. So the substrate fits well in the active site after the conformational change has taken place. So I have uploaded a different video, a separate video for Michaelis-Menten equation. So I have derived an expression for Michaelis-Menten equation. So there is a graph which I left out over here, that is here. The rate or the velocity of the enzyme catalyzed reaction as a function of substrate concentration you have to draw. The curve is a rectangular hyperbola. The Km is the Michaelis constant. The substrate concentration at half maximal velocity, which correspond to Vmax by 2. There is one more graph which talk about the order of the reaction. If you take a very low substrate concentration, Km will be far greater than the substrate concentration, and the rate of the reaction is first order for the with respect to the substrate. So the rate of the reaction could be K into molar concentration of substrate, where K is K2 divided by K1 into K1 plus K2 divided by ET. At high substrate, and here the notable point it is, the rate of the reaction is first order over here, whereas the concentration is very high with respect to Michaelis constant. The rate of the reaction is zero order with respect to the molar concentration of the substrate. So the rate of the reaction could be written as is equal to K dash into K dash, that is K dash is equal to K2 into ET. It is the total concentration of the enzyme, and the notable point over here is when the substrate concentration is very high comparing to the Michaelis constant, the order of the reaction is zero order reaction. Now let us get into heterogeneous catalysis. The catalytic process in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Catalytic oxidation of carbon monoxide on the surface of the noble metals such as platinum, palladium and rhodium is an example. The carbon monoxide and nitric oxide found in the automobile emissions are partially responsible for the formation of photochemical smog. Automobiles are now equipped with catalytic converters containing a mixture of catalyst to reduce these emissions through the reaction. A method by which this process is believed to occur on the rhodium surface. So this happens on the rhodium surface. So it is a heterogeneous catalysis. So, what is the mechanism of heterogeneous catalysis? If you ask, what will happen? The carbon monoxide and nitrogen monoxide will get adsorbed on the surface of the rhodium catalyst. Then they diffuse close to each other. They get diffused. And once they get diffused, means once they come close to each other, the reaction happens, the combination reaction happens, where the carbon monoxide and oxygen to form carbon dioxide and nitrogen to form N2 along with the desorption process. Once the product is getting produced, they will no more stay back on the surface of the catalyst, and the dissociation and combination process are equivalent to the reaction step. Heterogeneous catalysis, if you see, for example, with respect to the iron catalyst, if the reaction is happening, as I have told before, the catalysis will show an alternative path so that the activation energy reduces, so that the rate of the reaction will get increased. The catalyst induces a less difficult path for the molecule to follow. This is how the enzymes or catalyst enhances the rate of the reaction. So this is the new reaction intermediate where catalyst is involved. So instead of this much activation energy, then now the activation energy has reduced to this extent.